This is section 3.9. I'm on page 30 in our notes. This example says 2 men are standing 20 feet apart on opposite sides of the street. So I have my 2 men drawn opposite sides of the street 20 feet apart. One starts walking north towards work at a rate of 4 feet per second. So he's moving at a rate of 4 feet per second. And the other is a jogger, but he must wait for the signal to change. 2 seconds after the man starts walking to work, the jogger begins to run south at a rate of 10 feet per second. At what rate are the 2 men moving apart 5 seconds after the man starts walking to work? So this man, the worker, is walking for 5 seconds, whereas the jogger has to wait 2 seconds before he can go, and then he starts running. So he's only running for 3 seconds. I'm going to let X equal my jogger and Y equal my runner. So the worker walks for a total of 5 seconds. And again, that jogger had to wait 2 seconds before the light changed, and then he ran for 3 seconds. So we do know some stuff. If I let X equal my jogger and Y equal my worker, I do know that dx dt, the rate at which that jogger is running, is 10 feet per second. And I do know that dy dt, which is the rate that that worker is moving at, is walking at, is 4 feet per second. So it wants us to find at what rate are the 2 men moving apart 5 seconds after the man starts walking to work. So that distance in between the 2 men as they're moving apart is the diagonal distance here. And I'm going to call that Z. So it wants us to find dz dt when our time is equal to 5 seconds. Well, when time is equal to 5 seconds, how far did the worker walk? So if he's walking at 4 feet every second and he walks for 5 seconds, that means that he walked a total of 20 feet. And so this would be the distance of our worker, which is y. So when t is 5 seconds, we know that y is equal to 20 feet. Likewise, the jogger had to wait 2 seconds, so he was only running for 3 seconds, but he's traveling much faster at 10 feet per second. So he went a total of 30 feet. And the jogger is our x value. So looking at, I need now an equation to actually set this up, but looking at our diagram here, you actually have a triangle, if you guys can see it. This distance down here is just 20. And then this side over here, this vertical distance over here, is what the jogger was moving at. It's the same size as that other side over there. So I'm going to redraw my triangle without all my pictures of people and everything else, all those numbers on there. So redrawing the triangle. It is a right triangle. And that horizontal distance at the bottom is just 20. The diagonal distance that we had there is z. we have our distance at the top and a distance at the bottom. That distance at the top was the distance that the worker was walking, and we called the worker y. And the distance, the other distance that we have, the other vertical distance, is the jogger's distance, which we're calling x. And so we know at time 5 seconds that x was equal to 30 and y is equal to 20. So we can actually figure out that distance of z. So using that Pythagorean theorem, I'm going to have the distance of 20 squared plus 20 plus 30 is 50 squared equals z squared. And again, just by adding x and y, you get 50. And then working this out, we get z is equal to the square root of 2,900, which simplifies, and again, it's a distance, so it's only positive, to 10 square root of 29 feet. So at 5 seconds, we knew y was 20 feet, x is 30 feet, and z is equal to 10 square root 29 feet. So now I need to set up an equation for this. In order to do that, I'm not going to look at the time when we had 20 seconds and when we had 30 seconds, sorry, not seconds, but feet for my distances. I'm going to look at them as variables because those are changing. Those men are both moving at rates. And so to set up my equation, I am going to have my horizontal distance down here, which is 20. So I have 20 squared. I'm using that Pythagorean theorem again. Plus my vertical distance, which is going to be x plus y squared, is equal to z squared. So taking the derivative of 20 squared, that's just a constant, would be 0, plus taking the derivative of x plus y quantity squared, it's going to require me to use the chain rule. So I'm going to pull that 2 out in front, keep the inside function the same, raised to the first power, times the derivative with respect to time of the inside function. So taking the derivative of x with respect to t is just dx dt, plus taking the derivative of y with respect to t is going to become dy dt, equals the derivative of z squared with respect to t is going to become 2z dz dt. From here we can substitute in the values that we have. You can clean this up a little bit too if you would like. So we had x and y and z up above, and our rates dx, dy, and we have dz is what we're actually looking for. And both of those rates, the dx and the dy of t, are both positive because they're both increasing distances. They're not decreasing. So we have 2. And again, you can divide both sides by 2. We'll just get rid of those. We have x plus y, and x was 30. Y was 20. Dx dt is 10. Plus dy dt is 4. Equals z, which is 10 square root of 29, times dz dt, which is what we're actually looking for in this problem. So we need to solve this. Simplifying this in steps, we have 50 times 14 equals 10 square root of 29 times dz dt. And then simplifying this and solving for dz dt, we get 70 over the square root of 29. Again, you do not need to rationalize this. If you want to, you can. It's the same, it's equivalent answers. DZ, the distance we're talking about is feet. Over the change in time there is in seconds. So the distance between the two men is changing at a rate of 7